Hello, everybody. Welcome to another session of Lógicos in Quarentena. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to introduce Professor Stéphane Lengrand, who kindly accepted to give this talk. Stéphane, thank you very much.
Thank you. Yeah, so today I'm going to talk about realizability semantics of abstract focusing. So I'm going to describe what these things mean, but just as a forward, when I was very kindly invited to give a talk at this seminar, Valeria and Bruno expressed some interest in constructive view of classical logic or computational interpretation of classical proofs, and I thought, oh, that's a great topic, but I haven't really worked on the topic in a while. But you know, I did work on this for a number of years, and in retrospect, I think I've got something to take away from what I was working on, basically. And at the end of the day, when I think back on this, there are really two concepts that have helped me understand the computational content of proofs in general, and in particular of classical proofs. And these two concepts are polarities and focusing. So they were the topic of my habilitation thesis. So you know, if I give you those slides, then you can click on this link and get it from the internet. It's somewhere there. A journey from realizability to automated reasoning. And there's a part in it. So there's a big part which is a survey of computational interpretation of proofs, and in particular in classical logic. There's another part which is a bit more technical, a bit more novel, and it stems from the fascination that I have for something that's called the Adequacy Lemma. And I'm going to explain what that is. But basically, it's a property that relates typing to semantics. And by semantics, I mean more precisely a set-theoretic interpretation of types. I mean, the first thing I say when I try to explain to like a student what typing is to use his intuition about set theory. You know, this element isn't that set. Well, you can abstract this away to something a bit more syntactic. This element has that type. But there's definitely a set theoretic intuition and technically a set theoretic interpretation of types that, you know, with which you can interpret typing. Now, the adequacy lemma is proved over and over in the literature for many systems, and you know, I've done a couple of these proofs. It's called a lemma because usually it's not the end result that you want. It's a lemma that helps you prove something else, and typically that would be something like consistency or strong normalization. I've even seen adequacy lemma being used to prove confluence. So that's why it's called a lemma. But basically, after having seen so many versions of this adequacy lemma, I was starting to think, well, you know, is this a, you know, an informal methodology that we use and reuse all the time, or can we actually go a bit further and try to mathematically characterize, you know, what's at the core of this adequacy lemma, at least of the argument of the adequacy lemma? You know, trying to prove it at a very abstract level once and for all, and then all of the various versions of the adequacy lemma that exist, just, you know, derive them as instances of this you know, abstract adequacy lemma. You know, it's like one adequacy lemma to rule them all. So I'm not claiming that I've reached that, but I've tried to abstract and understand the core of this lemma as much as I could, and just to reduce the argument to its essential part. Now, that somehow is related to polarities and focusing, and this is what this talk is going to be about. Right, so focusing. So this is a logic seminar, so some people may be familiar with focusing. I know that you know, Valeria, Elaine, and Carlos, a lot of people are, but to anybody else, focusing is basically a notion of normal form for proofs in the sequent calculus. And it's a notion of normal form that is based or that exploits a notion for formulae that is called the notion of polarity. It originates from work by Andreoli in linear logic, with motivations for logic programming, i.e. proof search. And working with normal forms for proofs has an immediate and clear interest if you're trying to do proof search. Instead of searching for any kind of proof, you're just searching for proofs in normal forms, or focused proofs that are focused. So that narrows down the search space. That's why there's an interest in using focusing for proof search. That is assuming that every proof can be turned into a focused proof. Like that, for every proof there exists a proof in normal form or focused of the same thing. If that's the case, you can just restrict your attention to focused proofs and remain complete logically. Now, the notion of focusing and polarities, those notions have been studied in the context of, in other contexts, intuitionistic and classical logics, and not necessarily for logic programming or proof search, but also just to understand the semantics of proofs. Works by Girard, Danos, Joannet, Schellings, myself and my advisor, Roy Dickoff, Leong and Miller, and there are many, many other citations I could give there. So going back to the question of how to interpret, how to understand the computational content of proofs in general, usually this is done by understanding an operational semantics of proofs. There's also obviously a denotational semantics for proof that you can study, but there's a very clear candidate for an operational semantics of proofs in the sequent calculus, and this natural candidate is cut elimination. Cut elimination is a process that takes a proof with the notion of cut. So the notion of cut is a generalization of the notion of lemma. So you have a proof that that's decomposed into two parts. One part is proving a lemma, the other part is using the lemma. So that's a cut. And it's very natural to think that you can get rid of those cuts, get rid of using lemmas and prove things directly. And the fact that cuts can be eliminated from proofs is usually true in many logics. And that's one of the main activities that we do in proof theory. You come up with a logic and you show that cuts are admissible, or that cuts can be eliminated by some kind of procedure. And the procedure that you use for that can be seen as an operational semantics for proofs. Now, this is made very concrete and perhaps more natural in the context of the Curry-Howard correspondence. So in that context, you can see propositions as types or types as propositions, and you can see proofs as typed programs, or vice versa, typed programs as proofs. In other words, a proof of a formula A can be seen as a typing derivation for a proof term T of type A. So something that is usually expressed with this kind of judgment. T has type A in a typing context gamma. And on the logic side, the typing context gamma would be a context of a hypothesis that you reasoned from. Now, in that context, eliminating cuts in your proof can be seen as normalizing the proof term T. Okay, so T can be seen as a program. Its operational semantics, it has an operational semantics that corresponds to eliminating cuts in T. So basically, when trying to understand the semantics of proofs, we may as well try to understand the semantics of programs going through this Curry-Howard correspondence. Now, the role of focusing here is to help us design or understand first the operational semantics of proofs, and then the denotational semantics of proofs. Now, in the original context of the Curry-Howard correspondence, in basically the simply typed lambda calculus, this notion of normalization is very clear. It's given by what's known as beta reduction for the lambda calculus. Now, when your logical framework is not what would be the logic that corresponds to the simply typed lambda calculus, which is minimal natural deduction. If you're not in that context, but if you're in a slightly different context, for instance, you're not in natural deduction, but you're in the sequent calculus, perhaps you're not just dealing with implication, but you're dealing with other connectives. What this co-elimination process is and what kind of normalization you are going to apply in proof terms may be less clear than for the pure lambda calculus. And to clarify this, focusing can help. Okay, so that's where I find it useful. In particular, focusing connects computational interpretations of co-elimination to concepts that are well known in functional programming, such as call by name, call by value, pattern matching, etc. So it really helps establishing this connection between something that's pure logic, co-elimination, with something that's more like functional programming. Okay, so that was focusing. I haven't really said what it is yet, but just why it's interesting. And in my title, I talk about the realizability semantics of abstract focusing. So what is realizability? Originally, it was used by Clini and others after him to basically provide some kind of justification for constructive provability. So that kind of justification is done through the notion of realizer. And a realizer is going to witness the provability, the constructive provability of a formula. So something that is sometimes denoted like this. Actually, I think I got this symbol wrong. It's usually 2 horizontal lines and 1 vertical one. Anyway, and here we say that R is a realizer of A. You can see the formula A as the set of its realizers, in which case you just say that R is within the set-theoretic interpretation of formula A as a set of realizers. So for instance, a typical way of understanding implication, A implies B, in terms of constructive probability, is to define the set of realizers of A implies B as the set of computational functions from the realizers of A to the realizers of B. Okay, so if you have such a computable function, and if somebody gives you a realizer of A, then by applying the function to the realizer of A, you get a realizer of B, and that is basically witnessing the modus ponens. Now, in this notion of realizability, it's important to realize that, well, to remark that realizability is defined by induction on the formula A itself. So you define how realizers realize A by having previously defined what it means to realize the subformulae of A. And it's typically the case here with implication A implies B. The computational functions, these are the computational functions from the realizers of A, which is a subformula of A implies B, to the realizers of B, which is another subformula of A implies B. Now that's slightly different from typing, because if you look at typing, it's also a binary relation between things that are, in that case, terms and formulae or types. And this is usually defined inductively, but the induction usually follows the structure of the term T, not the structure of the formula or the type A. So there's a main difference there. Now, fortunately, there's a link between the notion of typing and the notion of realizability, and it's exactly the thing I was talking at the very beginning, namely the adequacy lemma. So in general, what the adequacy lemma says is if T has type A, then if you take the set-theoretic interpretation of A, And if you take the semantics of the term T, then you find that the semantics of T belongs to the semantics of A. In other words, the semantics of T is a realizer of A. Okay, so if I say in a shorter way, if T is of type A, then T realizes A. It's a short way of saying it, which is not so wrong in that very, very often what I denote here as the semantics of T is just T itself. In many, many cases, the realizers are actually the terms themselves, but they don't have to be. Now, the interest in realizability, yep. Is there a question?
Yes, I do have a question.
Yeah.
The question is adequacy of what? I mean, are we kind of thinking that the types are the primary things and the terms we're going to make adequate to it, or vice versa? So when you say adequacy lemma, what is the adequacy that we are talking of?
It's basically, I mean, the way I understand it is that it's the adequacy of the typing rules. If you think that what's given primarily is the semantics of formulae as sets of realizers, imagine that this is given to you. You want to show that the syntactic notion of typing given by the typing rules is kind of sound in the sense that whatever happens with the typing rules indeed reflect something that happens in the semantics. So the typing rules are adequate with respect to the semantics if you see the semantics as given prior to the typing rules.
Okay, but there is still a problem for me because, we are only thinking of beta reduction, not beta eta. So we kind of making a design decision kind of already about not only the rules, the typing rules, but also the quality of the typing.
Yes, I mean, the definition of the realizability relation already makes a lot of choices.
Right.
Okay. There's rarely, just one way of defining realizability. It's something that you can tweak and tune in various ways. So on this slide, I'm staying kind of abstract about exactly which system I'm talking about, precisely because I want to give an intuition about the adequacy lemma, irrespective of which system we're talking about. But you're right, there are many ways of defining realizability. There are many ways of defining typing. There are many typing systems you can talk about. And it's just, you have those two notions and you want to show that they're connected in this way.
Okay, thank you.
So the notion of realizability has been revived 20 years ago by work by Krivine on classical realizability. And this work is, interestingly enough, based on a notion of orthogonality relation between realizers and something that we can call counter-realizers. If you want to think in terms of proofs, these are proofs and counter-proofs. We can develop this, but basically, the same notion of orthogonality relation appears in the semantics of linear logic, as well as in many proofs of normalization for lambda calculi and classical extensions thereof. In particular, work by Parigot, work that I did as well. The notion of orthogonality comes back very often. Now, why should we study the notion of realizability in connection with the notion of focusing? Well, the thing that attracted my curiosity was that both the notion of realizability, especially with using orthogonality, and the notion of focusing use or exploit the notion of polarity for formulae. They exploit it in that there's something, there are some formulae that are positive, some formulae that are negative, and both realizability and focusing have an asymmetric treatment of positive and negative formulae. So I was struck by a paper by Guillaume Munch in 2009 that was connecting focused class. Sorry, that was connecting a sequent calculus for classical logic with realizability semantics via the notion of focusing. So the sequent calculus for classical logic included both focused and unfocused proofs. There was a notion of cut elimination that was doing more than just eliminating cuts. They were also normalizing all proofs into focused proofs. And that notion of operational semantics for proofs, or that computation or interpretation of proofs, was given a semantics in terms of realizability. And again, the key result in this paper was the adequacy lemma. So what I wanted to do is to try and describe the connection between the way focusing exploits polarities and the way that realizability exploits polarities. And I wanted to do this as abstractly as possible, meaning as free as possible from the idiosyncrasies of specific logic, specific connectives, of proof terms, realizers, etc. I wanted to sort of concentrate on the core argument. So in other words, what I wanted to do is to prove the adequacy lemma as generically as possible. Okay, so let me be a bit more concrete about polarities and focusing. Let's dig into a sequent calculus for classical logic with polarities. So every connective, in that case conjunction and disjunction, is annotated with a polarity, plus or minus. And every atom is also either positive or negative. Yeah, that's about it. I'm thinking in terms of I'm not including negation because I'm already thinking in terms of a sort of one-sided sequent calculus using De Morgan laws to define negation. So the involutive negation that you can see between atoms from P to not P and from not P to P can be generalized to all formulae by and the De Morgan negation would map a positive formula P to its negation, which would be negative, and it would map a negative formula N to its negation, which would be positive. So negation is flipping between positives and negatives. You can see implication A implies B as an abbreviation for not A or B, the or being a negative or. And what's the intuition behind the those polarities? The intuition is that negative connectives will have invertible introduction rules, and positives are the negations of those, and may or may not have invertible introduction rules. So, for instance, if you take the positive disjunction, you're trying to prove A1 or A2, you're going to have to prove either A1 or A2, okay, proving AI. With a negative disjunction, you are actually going to keep them both, sort of replace the disjunction as the sequent level comma, and then you can decide whether you do some more work on A1 or on A2, okay? So that's something that is very clear, for instance, in linear logic. But you can also already see this phenomenon in classical logic. So focusing here is going to be the ability to recursively chain the decomposition of positives without losing completeness. So imagine that you want to prove A1 or A2 or A3 with two positive disjunctions, and you want to prove this, you make a choice of trying to prove it by proving the left-hand side, A1 or A2. Then you can assume without loss of generality that your next step will be to either go for A1 or for A2, instead of doing anything else in your sequence, like using a lemma or decomposing some other formula, etc. It's not clear, it's not obvious that by chaining the decomposition of the top level OR with the decomposition of the left OR, you retain completeness. Focusing is basically the property that doing this is actually still complete. All right, so here's a little focus system for classical logic. And it splits the rules into 3 groups. First group is the group of rules that allow you to prove a positive formula. Well, to prove a formula in a focused way. So, for instance, if you're trying, like I was describing before, if you're trying to prove A1 or A2 with a positive OR, then your premise is, well, now you have to prove AI. And it's up to you to choose which I, but you have to prove AI. If you want to prove A or B with a positive, A and B with a positive AND, then you are going to have to do 2 tasks, proving A and then proving B. But what's important is that the way that you prove those premises is still by decomposing A or decomposing B, or here decomposing AI. At the point when you actually finish this decomposition and you hit an atom, if you want to prove it in a focused way, then you have to find this atom in your context of hypothesis. Okay. The last thing that can happen is that while you decompose your formula, at some point you hit a negative formula n. And what happens then is that hitting a negative allows you to release the focus and turn into another kind of sequence, which is then going to be proved by the second group of rules here, which we call the asynchronous phase. So in the asynchronous phase, you have you're allowed to have several formulae on the right, and that's typically useful when you want to decompose a negative disjunction on the right. What I was saying before is that you just replace this disjunction by a sequent level comma. So that's how more than one formula can appear on the right-hand side of your sequence. The rule for the negative conjunction is pretty simple. Then what? Okay, and then when does that finish? Well, it finishes when you hit a positive formula, or when you hit an atom, a negative atom. In both cases, what's going to happen is that you're just going to store the positive formula or store the negative atom on the left-hand side of the sequence. So here I'm using a presentation in which the work that you're doing is on the right-hand side of the sequence, and the place where you're storing things that you can no longer decompose is on the left-hand side of the sequence. Now, after applying those 2 rules, you are going to end up emptying the right-hand side of your sequence. So once the right-hand side of your sequence is empty, the only thing that you can do is to pick a formula in your store, gamma, and place the focus on it. And you're typically going to focus on a positive formula. Okay. Are there any questions about this this sequent calculus? Is that something that looks weird? That looks.
I think not.
Okay, cool. On top of these rules, you can add the cut rule, which in that case would just be cutting a formula not P on the right with a formula P on which you have the focus here. In that case, you derive a sequence with no right-hand side. So the fact is that this rule is not needed for completeness. It can be eliminated. So what's interesting is that the system is sound and complete for classical logic, no matter how you put polarities on connectives and on atoms. So the polarities that you have on connectives and atoms, those polarities are only going to affect the shape of proofs, but not provability. Okay, so how does cautimation work in this context?
Stéphane, can I stop you a minute?
Yes.
I mean, the question is not about the sequent calculus as you presented, but the question is about the generic approach, because you started talking about Curry-Howard, and then you went and did something that you're not allowed to do in Curry-Howard, which is to transform the implication A implies B into not A or negative or B, right? So, yes. Because this is not intuitionistically valid, and then then the rest works for me. That's not a big deal, except that I don't have now a notion of real implication going on. This implication that you have going on there is fake, right? It's all about just conjunctions and disjunctions, and you're smuggling the negation because.
Yeah.
Okay.
So I could have an explicit notion of negation first. Here I don't have it. I mean, it's smuggled in the sense that essentially what I'm presenting here is a one-sided sequent calculus. I mean, I use two sides technically because I want to show that what I work on is on one side and where I store stuff is on the other side. But essentially, this is just a one-sided sequent calculus. And as is typical in one-sided sequent calculi, the negation is always taken to be the De Morgan negation.
Right. Doesn't that feel strange?
Not in classical logic. So here it's a classical system. I'm not pretending it's an intuitionistic system. So in the case of classical logic, I don't really have a problem encoding implication as not A or B.
Okay. Thank you. Just that we're all clear where we're going. Thank you.
Right. Yeah. But something that's always struck me is the fact that concatenation works. Every time you look at a logic and you look at the introduction rules, the elimination rules, or the left introduction rules, or the right introduction rules, and you cross your fingers and you hope that you can actually write the cut elimination procedure that's going to eliminate cuts. And every time it almost feels like a miracle. So here, typically, if you're trying to eliminate a cut where the formula P here is A1 or A2, then typically you would have the left premise be derived by this rule, and you would have the right premise derived by this focused rule, this synchronous rule. And it so happens that once you have those three premises, where depending on I, you can replace the cut that you had on the formula P by a cut on AI. And here you just select one of the two premises that you keep and that you're going to cut against AI, and you just throw away the other one. So in that case, it works. And then for other connectives, you do the same. And at the end of the day, you play this game and you feel lucky. Usually at the end, you still have to prove that your procedure terminates, but it's already to me a miracle that for every connective you can find a rewrite rule that will replace one cut by smaller cuts. So philosophers that, logicians in philosophy, they came up with this notion that there must be some kind of harmony between introduction rules and elimination rules, or between left introduction rules and right introduction rules. A notion of harmony that makes this cut elimination possible. And one thing that I was interested in is to, whether we can actually express this notion of harmony mathematically. All right. So when you prove cut elimination, you come up with a bunch of rewrite rules, like the one on the previous slide, and you have to show that your procedure terminates. You have to give some kind of termination argument. So maybe you replace a cut by cuts on smaller formulae. Usually that would do the trick. Or maybe if you're in natural deduction and dealing with the simply tapped on the calculus, your termination argument is going to be a bit more complicated. So one way of approaching the issue of termination is to actually construct a model that you use to prove termination. So that would be Girard's reducibility candidates for system F, let's say, and there are many other variants of that. One variant is using the notion of orthogonality I was talking about earlier. So you can consider a set of elements called realizers and interpret each proof as a realizer. Very often, the realizer will be the proof itself. You don't have to transform it too much. Then you have a notion, a binary notion of orthogonality between realizers, or between, say, realizers and counter realizers, and you interpret each formula as a set of realizers. How you do that is as follows. You do something asymmetric between positive formulae and negative formulae. So a positive formula, P, is first going to be interpreted as a set of basic realizers that follow the introduction rules for the formula P. And I'm going to give an example, I think, just... Well, okay. I'm going to give an example just after. And then what you do for negative formulae is not really to look at the introduction rules for n, for your negative formula, but you're going to define the interpretation by duality, by orthogonality. You're going to say, well, I have a negative formula. If I take the De Morgan dual of that negative formula, I get a positive formula. So that positive formula, I interpret it as shown above. So I've got a set of realizers for the De Morgan negation of my negative formula. Then I'm going to interpret my negative formula as all of those realizers that are orthogonal to the realizers of not n. So here I've got twice the same symbol, but they express different things. The first symbol here is the De Morgan dual of n. Okay, so this is a syntactic pass of the formula. And the orthogonality symbol here is the one that we use in geometry, like saying all of those things that are orthogonal to all of those things in here. Does that make sense? So you define the interpretation of a negative by duality rather than primitively. Now, if you are in a focused sequent calculus, that will suffice. If you're not in a focused system, then you may want other realizers for your positive formulae than those that follow the introduction rules. In that case, you close the construction by taking the bi-orthogonal of your original set of realizers. So you have an original set of realizers that just follow the introduction rules for P, and then you extend that set with a bi-orthogonal construction. Let's take an example with a formula that's negative. Okay, so if you have A implies B, which is negative, the way that you're going to interpret this is as follows. Well, you look at all of the how could you violate an implication? You would violate an implication if you can provide a realizer of A and you can violate B. All right. So what you're going to do is to consider those pairs of a realizer of A and a realizer of not B, something that justifies a violation of B. Okay. So you take those pairs, and these are all the bad guys, all the guys that could potentially witness that you do not have A implies B. And what you're going to do is to say that the realizers of A implies B are, well, anything that is orthogonal to those pairs TE. Okay. You can also see that TE is basically a realizer for the De Morgan dual of implication, which is known as subtraction. It's very rarely used, but it does exist, and it reflects the intro rule of subtraction. Okay. All right. But what's important here is that we've defined the realizers of A implies B by orthogonality to those things that could potentially witness that A implies B does not hold. We haven't really followed the syntax and the introduction rules for implication. So typically, the introduction rule for implication is witnessed by lambda construction. And this is not, the lambda construction is not involved in the definition at all. Okay. And the way that we do this in this order is because A implies B is negative. Okay. So the adequacy lemma would say that, with those definitions, is that if pi is a proof of A, potentially with Kurtz, then pi is a realizer of A, or pi as a realizer is in the interpretation of A according to those definitions. So you can re-express Girard's reducibility candidates with that terminology, with that vocabulary. It wouldn't change. It would be cosmetic, basically. But the good thing about expressing that kind of argument with realizers, set-theoretical interpretation of formulae, and orthogonality is that it generalizes beyond, say, system F or the intuitionistic case. You can apply the same technique for classical proofs. So basically, if from the adequacy lemma what you want to prove is cotermination, what you're going to do is that you are going to engineer the definition of the orthogonality relation so that being in the interpretation of A implies being able to reduce to a code-free proof. So in this whole approach, this binary relation orthogonality is up to you. It's a parameter. You can choose whichever relation you want. The adequacy lemma will hold. Okay. So if you want
clarification questions, clarification, because a clarification question. I don't think I understand very much this how the implication is working here. I think the normal way of thinking about it is happening on the T colon E, right? Because this is application, and so the lambda is built in there, kind of on the background. But but then you say, but then I want to take the orthogonality of that, and then I don't think I quite follow why we need orthogonality. Sorry, I'm being
typically T colon E is stacking argument T on top of the stack E. If you want to think in terms of lambda calculus, it's really you're building a stack of arguments for a function that's going to consume them. So a more traditional definition of the interpretation of A implies B, and I've given it earlier, is any computable function that takes a realizer of A and produces a realizer of B. So this is reflected here. T is a realizer of A, and E is something that that is a realizer of not B. So if you say the realizers of A implies B are anything that's orthogonal to that stack construction, then in particular, I mean, if you want to go that way, you could any computable function that transforms a realizer of A into a realizer of B would be in that orthogonal. Because if you put that function in front of this stack of arguments, it's going to consume T, which is a realizer of A. By definition, the function is going to output a realizer of B, and then the realizer of B will be facing the rest of the stack E. And since E is a realizer of not B, then the output of your function would be orthogonal to E. So this definition is capturing the more traditional one, and it's flexible in that it's not really specifying the syntax of what it is that is going to be orthogonal to that stack construct. It could be lambda, it could be another kind of function, it could be,
That was very helpful.
Thank you. Your question. Yeah. All right. So basically, the notion of orthogonality occurs or can occur in arguments for cotermination and strong normalization, even. And the lesson from using orthogonality there is that the meaning of positive formulae is primitive, is defined first in relation to the intro introduction rules, or in relation to the syntax of the realizers, whether it's an injection or a pair or something like this. And then the meaning of negative formulae is defined by duality as anything that is orthogonal to the realizers of the negation, of the negative negation. And this is, to me, something that that connects to this notion of harmony I was talking about earlier. You can reflect this lesson from orthogonality directly in the syntax by considering that the introduction rules of positive formulae are primitives. You commit to some introduction rules, whichever they are. And then if you want to have harmony with the introduction rules for the negatives, you'd better choose them carefully, because they have to be in harmony with the introduction rules for the positive. Even, I would say that you can automatically infer what the introduction rules for the negatives would be, if they are to be in harmony with the introduction rules for the positives. So there's an asymmetry there, which I think orthogonality gives light on. So basically, you give the intro rules for positives first, and then you just automatically infer the dual rules, just so that cotermination works. Okay, so in that case, cotermination is no longer a miracle. It's like you have it by design, okay, because you only define half of the rules, and the other half is inferred so that cotermination works. Okay, so this is a bit hand-wavy, and what I've been trying to do is to actually express those ideas in a formal mathematical context by developing some ideas from Noam Zeilberger. So here's the same system as before. I've already shown that slide. It's a focused sequent calculus for classical logic, and basically I want to abstract away from the idiosyncrasies of the connectives that are in here, of the fact that we are even dealing with classical logic. Can I extract a notion of focusing that's sufficiently abstract, for me to build an orthogonality or a realizability semantics independently from the actual connectives we're talking about, for instance? And here's what I came up with. So again, the rules are divided in 3 groups, following what we have for classical logic. And it kind of becomes much simpler. I mean, there are fewer rules, for one thing. In the first group, again, you're trying to prove something, a formula, with a focus on that formula. And what's going to happen is that you are given here, as a parameter, a way of decomposing this formula M into, let's say, smaller formulae. So typically, if I come back to the example of this positive formula here, A1 or A2 or A3. So you can decompose this into A3, into A1 by going for the left and then for the left, or by A2 by going for the left and then for the right. So you have different ways of decomposing this compound formula. And I imagine here, at an abstract level, that somebody is telling me, with an external relation, how to decompose formulae into smaller formulae. Yeah. So that relation is given here. So delta is here you can think of them as the collection of subformulae of M that result from one particular decomposition of M. Okay. So think of the delta as a, say, maybe a list of formulae that you hit at the end of your synchronous phase. So typically those formulae would be either atoms or negative formulae. And now once you've decomposed M into those, then you have to prove each of them. Okay, so from gamma, which is your actual original set of assumptions, you want to prove each of the formulae that results from this one particular decomposition of M. And that expresses the whole synchronous phase in one rule. Okay. Now, how do you prove that? How do you prove the things in delta? So delta, you can think of it as a list. Actually, it doesn't have to be a list. It can be something different. But if the list is empty, which I represent with this bullet, then you have nothing to do. Okay, so this is like a leaf of your proof tree. And if delta is made of two things, delta 1 and delta 2, you're going to have to prove delta 1 and you're going to prove delta 2. Okay, so those two rules are pretty simple. It's just you go through the formulae that you've accumulated or aggregated in delta. Now, the kind of formula that you find in delta, as I was saying, it's either an atom or a negative formula. In other words, the negation of a positive formula. So if you find an atom, remember you're at the end of your focused phase. You have no choice but to find the atom in gamma. This is the init rule. This is the second kind of leaf that you can have in your proof tree. Now, the interesting part is what you do when you find a negative formula, or let's say the negation of a positive formula. Remember there that we don't even know what connectives we're talking about. What is given to us is just a way of decomposing a positive formula into subformula. So the way that you're going to try and prove this negative formula, not M, is by ranging over all of the possible ways of decomposing it. And you can have many ways. And for each of them, you're going to have to show a contradiction, so an empty right-hand side, from your original context gamma, extended with those formulae that result from the decomposition of M. Okay, so this premise is a bit weird. It's a higher order premise because it's kind of universally quantified here. Meaning, if I have 42 ways of decomposing M into smaller formulae, I'm going to have 42 premises. Okay, so it's some kind of meta rule that here has a number of premises that depends on the number of ways in which you can decompose M. Okay, so this implication is not the object level implication. It's literally range over all the possible ways of decomposing your positive formula M, and for each of those ways you have one premise of that shape. Do you have any questions there?
It seems not.
Right. So imagine, for instance, that you have the negation of a positive disjunction. A positive disjunction, you have two canonical ways of proving it, by proving the left-hand side or by proving the right-hand side. So you have two ways of decomposing that disjunction, and for each of those two ways, you need to show a contradiction. So it's exactly a case analysis. Now, what does it mean to actually get a contradiction from a bunch of hypotheses? The way you do that is, again, by using the select rule. You pick something in gamma, and you place the focus on it. I mean, you place the focus on its negation. Okay, and you can add to this the cut elimination, the cut rule, which says that if on one side you have a proof of a negative, not M, and if on the other side you have a proof of the positive, M, then you can cut them and get a proof of a contradiction. Okay. But again, the point is that this cut rule is admissible. You can remove it. Okay. So basically, the idiosyncrasies of the connectives that you're talking about, they're hidden in the decomposition relation here that decomposes M into smaller formulae. And here I've indicated a P. P stands for pattern. You can imagine that if M is a positive conjunction, the proof of M is going to be made of two components. So the pattern here is a pair pattern made of two things. If M is a positive disjunction, then you have two canonical ways of proving it: the left injection and the right injection. So you're going to have two possible patterns for a positive disjunction. But the notion of pattern will become clearer when I introduce proof terms. So what's funny here is that if you look at the system, the notion of negation of involutive negation never really occurs. Here I've kind of switched back to an explicit negation symbol, and that actually allows me to only have syntax for positive formulae. I don't even need the syntax for negative formulae at all. Okay, so imagine that here M stands for positive formulae. At no point do I have to compute the De Morgan dual of an M. Yep.
Now I'm missing something again, because isn't the tilde there something that is the negative version of the M?
Isn't the what?
The tilde. The little.
It's not involutive. It's an actual. It's an actual symbol that is sticking there. It's I'm not transforming M into something. It's just a notation that's there to say I'm not trying to prove M. I'm trying to falsify M.
I see. But that's where it's hidden, right? Yeah.
Yes. I mean, this does mean negation in the sense that the sequence is stating gamma falsifies M. And you can think of it as, well, you can compute the De Morgan of M and then say that gamma proves M. Proves this De Morgan dual of M. But you don't have to think in that way. You can just read that sequence as gamma falsifies M.
Okay, thank you.
Now, since the connectives are actually hidden in this decomposition relation, you don't even need M to be made of syntax. I mean, here we're never really, I mean, I've said decompose, and in delta here, I've told you, delta are the subformula of M that result from the decomposition. But that's just me trying to help your intuition. It's, if you look at the system formally, there's no reason why M would even be made of syntax and would have subformulae. Okay, so M is just there ranging over a set, and because it's not necessarily syntax, that's why I've stopped calling it a formula, and instead I'm just saying M is a molecule. I just needed a word that's different from those that I use traditionally, because it doesn't have to be syntax. It doesn't have to be a formula with subformulae. And the notion of atom here, again, it doesn't have to be a particular kind of M. Okay, so you will find those atoms in as elements of this list delta. Yeah. So that's just to justify my change of vocabulary. Okay, so what else is present in this system? Here, at some point, I extend my context of hypotheses. Okay, I extend the context of hypotheses with those things that result from a decomposition of M. So I was wondering when I was developing the system, should I specify what this notion of extension is? It turns out that if you leave it abstract, unspecified, then that's one extra parameter that you can tune, and by tuning it, you can actually have instances of this abstract focusing system that captures different logics. So that was the realization. By tweaking how you extend gamma with a delta, you can actually either get classical logic or intuitionistic logic. Okay, so basically playing with the range of M, like what are molecules, with the range of atoms, with the decomposition relation, and with the notion of context extension, these are all a bunch of parameters that you can tune in order to capture a particular logic, a particular proof system, and hopefully the hope is that you can derive the meta properties of this particular system from the meta properties of the abstract system. Okay, so in particular, your notion of molecule, if you want to capture a one-sided sequent calculus or a two-sided sequent calculus, you can say that your molecules are not just formulae, but formulae with a little annotation that says whether they're sitting on the right-hand side or on the left-hand side of the sequence. Okay, that's how, for instance, you can capture a two-sided sequent calculus as an instance of this abstract system. And the system is engineered so that contamination works. It is also equipped with proof terms, and these are pretty natural. So I've said already that the way that you decompose a molecule into this delta can be captured by a notion of pattern. So if you have a positive disjunction, you would have injection patterns. If you have a positive conjunction, you would have a pair patterns. And because of focusing, you can have recursive patterns that have more than one layer of constructions. And then if you see that as a pattern, a proof of a focused proof of say positive formula M is going to be a pattern together with a particular way of inhabiting the holes of the pattern. Okay, and this particular way of inhabiting the holes of the pattern is denoted by D here. So D, which is witnessing why delta follows from gamma, is actually also saying how you inhabit the holes of the pattern P. The two rules for dealing with the lists are very natural. You have a basic construct for the empty list. You aggregate the justification of delta 1 and delta 2 in order to get the justification of delta 1 comma delta 2. If you want to prove an atom, and as I said before, in that case you have to find the atom in gamma, then you can use an indexing scheme in gamma to refer to different elements of gamma. You can use a variable for this and say that in gamma, this variable has type A, okay, and just indicating this variable is going to tell you how you justify why A is in gamma. And the most interesting rule is this one. So this one, remember, it's a rule with as many premises as you have ways of decomposing M into small things. So each of these ways is characterized by a pattern. And what you need here is to say, well, for each kind of pattern that helps you decompose M into smaller things, you have to produce a proof term witnessing a contradiction from gamma and delta. Okay? So if for each pattern P, you have to produce a term witnessing a contradiction, basically, you can collect all of these terms. You can see the set of these terms as a function that's going to take a P and return a proof term for the contradiction. And this is very much like the very original definition of realizability for implication. It's like it's a function that transforms realizers of A into realizers of B. So here we have a function that takes a pattern. The pattern is specifying how M is decomposed and mapping this P to a proof term for the contradiction from that context. So the function here, F, that does that, becomes the witness or the proof term for why gamma falsifies M. Now, select is simply, remember, so if you have an empty right-hand side, the way that you're going to produce a proof is to actually pick some element in gamma and place the focus on it. So picking an element in gamma means that you have to identify a variable, like x minus, whose type is a positive formula, and you're going to place the focus on it. So this is a focused sequence on the type of x minus in gamma, and then you're going to have a proof term to witness the focused proof of that. Okay, so the proof term for the contradiction is just a pair of two things. First, the variable that indicates which is the formula in gamma that you're going to place the focus on, and secondly, a proof term for the focused proof of that. In the case of a cut, it's very similar. the second premise is exactly the same. You're placing the focus on M, so you're going to have a proof term witnessing a focused proof of M. And then on the left-hand side, you're going to have a falsification of M from gamma. And we've already seen that a falsification of M from gamma is witnessed by a function that's doing this mapping from patterns to proofs of contradiction. So you place this function face-to-face with an actual proof term for the focused proof of M. And at that point, I should probably ask whether there are questions about this, at least compared to the system without proof terms, if intuition match or no? Okay. So how do we do cut elimination? Basically, the kind of construct that we have to reduce is this. Okay, we have a function facing a proof term witnessing a focused proof of M. Okay. Oh, so if you look at the focused proofs of M, how they look like, it's always a pattern, P, and a way to fill the holes of the pattern, D. So when you look at the kind of construct that you have to eliminate, it's always a function witnessing the fact that a context falsifies a positive formula, face-to-face with a pattern and a way of decomposing the pattern. Now, how are you going to eliminate that construction? Well, fortunately, f is a function that's able to consume a pattern and produce a proof of contradiction. So you're going to reduce that construct to f of p. That's going to be a proof of contradiction, but in an extended context in which you have like more variables. So the way that you instantiate those variables is exactly what D indicates. So that construct reduces to f of p substituted by D for a notion of substitution. So the cleanest way of specifying this notion of substitution, or specifying more generally how to reduce proof terms and therefore how to eliminate cuts, is via a notion of abstract machine. So an abstract machine is going to have two things. The first thing on the left here is the proof term that you want to reduce. And because it's an abstract machine, the second thing is an environment rho that's telling you how to interpret the free variables of this proof term. So the way that you reduce this construct in the context of a particular evaluation environment rho is simply by applying f to p. There you get a proof term, and you have to evaluate that now, not in rho, but in rho extended with D, or the interpretation of D under rho. Okay. So, I mean, I don't want to spend too much time here, but there's something like beta reduction that naturally arises from the system. Okay. And now, for the system, we can develop a realizability semantics that's going to help us prove that the system, that the cut elimination terminates. And it's basically turning all the notions that we have seen so far into semantical ones. So you interpret the system in what I call a realizability algebra, and that's pretty similar to the notion of realizability algebra that Krivine has developed around about the same time. Here, the notion of realizability algebra is made of a set of things with which you are going to interpret the positive variables. So those variables whose types are molecules or are positive formulae, let's say. Oh, sorry. So this is a set of denotations just for variables. Then you are going to have a set P to interpret all proof terms for witnessing proofs of molecules, so positive formulae. And then you're going to have a set N for negative denotations, so where you're going to interpret all refutations of molecules. And then you have an orthogonality relation between P and N. Now you need a way of interpreting pattern. So the notion of pattern and the notion of decomposition, remember, it's a parameter of the whole system, And by tweaking this parameter, you're going to capture different connectives in classical and intuitionistic logic. So at some point, you need to give a semantics to the notion of pattern in the similar abstract way. And basically, you're going to interpret each pattern as a collection of elements from L, as a function that maps collections of elements from L and N. So these are the things with which you're going to interpret the leaves or the wholes of the pattern to a denotation in P. So a pattern is a function that takes as input the way that you fill in the holes or the denotations thereof, and it's going to map that to a positive denotation. This is going to be the semantic interpretation of a pattern. And then similarly to the notion of hypothesis context, you're going to have to use a notion of semantic context, mapping variables to variable denotations and mapping negative variables to negative denotations. Okay. And similarly to the context of hypotheses, which must be extendable with new hypotheses, the same happens on the semantic side. This semantic context also needs to be extendable. Okay, I'm going to go a little bit faster here, but basically, you do exactly like we did in the early slides to define realizability semantics. Is first define the interpretation of positive formulae, or interpret the formula as a set of realizers. And this is going to be given by the syntax, pretty much by looking at the different patterns that can decompose M into smaller things. So that's the condition here. The pattern P is helping you decompose M into smaller things. So that's really following the introduction rules of the positive. And the negative interpretation of M is going to be defined by orthogonality. So you're going to say the negative interpretation of M is anything, any negative denotation, which is orthogonal to the positive, to the realizers in the positive interpretation of M. Okay, so this is really the definition by orthogonality instead of a definition following the introduction rule. So there is really the asymmetry that I was already talking about earlier on a particular example of a classical focused sequent calculus, but which is here captured at a much more abstract level. Okay, this is what I want to focus on. There's one thing, which is that if you want the definitions to make sense, at some point you actually need some kind of well-foundedness property, meaning that when you do decompose a molecule M into components delta, those things in delta are really smaller than M according to a well-founded order. If you do not have this well-founded ordering, saying that whatever you decompose M in is actually smaller, then you have loops. I mean, you cannot set up the definitions in a well-formed way. Okay, so I'm going to skip a little bit to have directly the adequacy lemma. So this is kind of my version of the adequacy lemma to rule them all. It's an adequacy lemma that's proved at this level of this abstract focusing system. And by instantiating the various parameters of this abstract focusing system, then you recover the adequacy lemma for various known systems like a focused classical sequent calculus, one-sided, two-sided, or an intuitionistic sequent calculus, etc., etc. So the conclusion of the adequacy lemma is, again, that if you have, say, a proof T of a contradiction, then the semantics of T is really in the orthogonality relation. Like if you look at positive sequence, like the focus sequence, if you have a derivation that a focused proof of M with proof term T plus, then the semantics of T plus really belongs to the positive semantics of M. So these are the three statements that you need to get the induction to go through. But are really capturing the the notion of adequacy at an abstract level. Now, this only holds if three hypotheses hold. The first one, I've already talked about it. It's the well-foundedness. You need to know that when you decompose a molecule M into smaller things, these things are really smaller according to a well-founded order. The second condition is stability, and that's something that is already known in orthogonality models. When I said earlier that you could take the orthogonality relation exactly the way you want, it's not completely true. This orthogonality relation usually needs to be closed under anti-reduction. So by backward reduction, say if your system is the lambda calculus with beta reduction, you need your orthogonality relation to be closed under anti-beta reduction. So if the results of beta reduction is in the orthogonality relation, then the original lambda term is also in the orthogonality relation. So this notion of stability, backward stability, is also essential here at the abstract level. The third condition that is a bit new is context correlation. There is a notion of context of hypotheses. So when you have a context of hypothesis gamma, you can extend it with new hypotheses. And then there's a semantic notion of context, which is the way I interpret my variables. If you give me some extra variables, I should be able to extend my context with interpretations for those new variables. And those two notions of extensions, which work on different kinds of contexts, a priori, they have no reason to be connected to one another. So for the adequacy proof to work, you actually need to connect those two in this way. So if rho is in the interpretation of gamma and delta is in the interpretation of delta, then the extension of rho with delta belongs to the interpretation of the extension of gamma with delta. It's very reasonable. It's just the only way to connect those two notions, the syntactic and the semantic notion of context. Okay, and that's exactly what I described. Applications. You have this adequacy lemma that holds for many kinds of realizability algebras. You're free to choose your orthogonality relation, but also the set of denotations as you wish. So one particular way of doing that is to pick a realizability algebra that helps you conclude consistency. For this, you just need what I call a Boolean model, i.e. a model in which the orthogonality relation is the empty set. Nothing is orthogonal to anything. Okay. So in that case, the interpretation of your negative formulae is either everybody or no one. Okay, depending on whether the positive interpretation of molecules is empty or not. So it's really binary. It's either you've got all denotations or an empty set, the way you interpret a formula. If you look at what the adequacy lemma says in that particular case, since the orthogonality relation is empty, it means that can you have a proof of contradiction in the empty context? No, you can't, because if you did, then the adequacy lemma would tell you that the interpretation of T belongs to the interpretation of the orthogonality relation, which is, in that case, the empty set. And that's impossible. So you immediately have, as a consequence of your adequacy lemma, the consistency of the logic. Okay. You can use a different kind of realizability algebra to prove the normalization property of cotermination. It's just giving different a slightly more subtle notion of orthogonality relation than the one used for the Boolean model. And again, just the adequacy lemma, if you look at what it's going to say, it's going to conclude that all of your terms are strongly normalizable. Okay, and this is the takeaway slide because I've been far too long. Basically, I want to compare typing with realizability. In typing, inhabiting a positive formula means that your inhabitant is basically a pattern with a way of filling the holes of the pattern. Okay, and on the semantic side, it's very similar. The way that you inhabit the set-theoretic interpretation of a formula is also by having your denotation here be constructed from the semantic version of a pattern and the semantic version of how to fill its holes. So for the proofs of positives, typing and realizability say pretty much the same thing. For the negatives, there's a main difference. If you look at typing, what it means to actually falsify M is to say, well, give me any pattern P explaining how M decomposes into delta. And for each of those patterns, I need to construct a proof of contradiction. If you look at realizability, if you look at the way that the negative interpretation of a molecule is defined, it means that you are in the negative interpretation of M if you are orthogonal to anybody in the positive interpretation of M. So in particular, you should be orthogonal to every PD which would be in the positive interpretation of M. Now, the main difference between the two is that in typing, your function f that's supposed to give you proof of contradiction is a function only of the pattern. It looks at the pattern, and just according to the pattern, it should be able to build a proof of contradiction, no matter really what delta is, or not really looking into delta could be proved. Okay, so there's some kind of uniformity here in which you can do something completely different from one pattern to the next, but you have to ignore really how the holes of the patterns are filled, or you have to treat the holes of the pattern in a uniform way. You can't really inspect how the proofs, how the holes of the patterns are filled in order to decide how you prove your contradiction. Whereas in realizability, since you're saying, well, it's anybody who's orthogonal to those dudes, P and D, then then you are allowed to not only look at the pattern, but also look at how its holes are filled and do one thing or another depending on that. So it's basically the depth, of how far inside the positive term you're allowed to look in order to build your proof of contradiction that separates typing and realizability. All right. And the difference is a bit similar to how you prove a for all. Like in logic, typically you prove a for all by introducing an eigenvariable and reasoning about that eigenvariable sort of parametrically. I mean, the fact that it is a variable makes your reasoning about it completely uniform. You're not really inspecting which n it is. I mean, n here, if it's arithmetic, yeah, you could go into you could inspect which number n is. But in general, if you're talking about sort of pure predicate logic and you have a for all quantifier, you cannot produce one proof or another depending on this quantified variable. You really treat it as a variable, and that's different from, say, the omega rule that you could use in arithmetic, in which the omega rule is ruled by Frege and Schutter, that allows you to prove for all NA by explaining how you prove A of 0, A of 1, A of 2, etc., and have an infinite number of subproofs that could potentially do something completely different from one integer n to the next, so that the numbers wouldn't be treated uniformly. You could actually do something that's sort of customized to the number that you're dealing with. So the difference between the symbolic abstract handling of eigenvariables and the omega rule of Schutter is exactly the same difference that you find between typing and realizability. Typing is only allowed to look at the pattern and cannot inspect how you fill the holes of the pattern. It has to treat them uniformly, whereas realizability can look at the pattern and look at how the holes are filled in order to produce a proof of contradiction. And that's basically it. So the whole theory of abstract focusing has I've formalized in Conc to make sure that my proofs actually do go through. I've done it with a first-order version of this. I mean, on those slides, I've only presented propositional logic, but it is possible to extend it to first-order logic with actual quantifiers within formulae. Proving head normalization, strong normalization is still on paper and not in calc, because then for strong normalization, you need to formalize in calc what it means to reduce under lambda or whatever equivalence of under lambda we have in abstract focusing. It has strong connection with Ludix, this abstract focusing framework. But again, abstract focusing to me is a framework with lots of parameters that you can instantiate in order to get different systems. And that's not really how Ludix works. It's like one system. And on that note, I'm going to stop and ask if you have any more questions.
Thank you very much, Stéphane. So now we have some time for questions, comments. Stéphane, just a curiosity, is this the code available?
Yeah, it's if you go to my homepage, the code proofs of part 2 are available. Now, when I did those code proofs, it may not be the last version of Coq, so I can't guarantee that they would still go through in the latest version of Coq. I think I used Coq 8.7.
With 8.7, probably it will work.
Okay.
I'm almost sure that it will work.
Okay. But yeah, it's got the so chapter 4 is the propositional version, which is what I present on those slides. Chapter 5 is the system for first order logic, so with quantifiers, and that's actually the thing that I model in Coq. And then chapter 6 is about the semantics, the realisability models, and the adequacy lemma. And chapter 7 is using the adequacy lemma to prove stuff about normalization, elimination, etc.
Valeria?
Sorry, I just need to kind of go back to. Yes, I got it. So lovely, Stéphane, really very good. I think I understand an awful lot more now than I did before. But I have two questions that are not very well thought through. The first one is, there's an awful lot of work that's being done by the orthogonality, and as usual, I would like to kind of understand that better. So I understand that it is a parameter, and I think another time I would like to see the proof that this works for intuitionistic logic, because it's kind of there again, you don't have naturally an orthogonality. But I'll let it go, because I think I mean, I'm sorry, but I have a meeting to go in a minute. So my important question is about realizability. It's about doing categorical semantics, but without the morphisms, right? Because the realizers are all completely, they are not connected by, not even posets. They are not even, this is less, realizes less than that. They're just numbers. So the question is, so realizers are wannabe categories, or wannabe posets, because eventually you do want to I think you do want to kind of be able to tell when proofs are different by saying, the realizer in this direction is less than equal than the realizer on this other direction, or kind of, if we are going in a direction. So the question is this going to extend if assuming we could do it, right? Which I have no idea if we cannot.
I don't know either, but historically, realizability has usually been defined with very concrete notions of realizers. So Originally in Clean's works, it's like with the theory of computability, so it's like computable functions, or they're Gödel numbers. So it's as you were saying, just like numbers. Later, we realized that you could take the lambda terms themselves as realizers, so it's something still very syntactic, or you can take the proofs themselves if you are not in the lambda calculus, again something syntactic. So it's true that traditionally a realizability semantics is not really a semantics in the denotational sense. It's still very much based on syntax. The way you define realizers, if they're still lambda terms or numbers. Now, in what I did here, since I've kind of abstracted away the notion of realizability algebra to leave the door open to having realizers that were not made of syntax, that could be made of something much more denotational, morphisms, or something that could have structure of poset or something. So just simply by opening the door to having realizers be something else than just syntax, I think that's a step in the direction of possibly using much more interesting algebraic structures, categorical structures for those realizers. But I haven't really pursued that or done it.
Oh, that's great. Thank you. That's as I was saying, I do love the idea of kind of abstracting over the two relations and showing how the abstraction works. Pretty good. Excellent. Thank you.
Any other question or comment?
Hi, Stéphane.
Hi.
No, I had a question before, but I think you mentioned that in the conclusion. So now you have also this for first order logics as well, because I think that last time I talked to you about it, you only propositional and mostly classical. But as I see now, you can apply this to first order and well, classical, intuitionistic, and what else? I mean, can you handle like substructural logics as well, or this is?
No, it's a very good question. Yes, so I can handle first order logic with quantifiers, and there's actually a nice story there in that if you define everything by orthogonality or by duality, let's say, and you say that the way that you prove there exists X such that A is simply by giving a pair of a witness for X, a first order term T, together with a proof of A of X, well, A of T, I guess. So that's a natural way of explaining how to prove that there exists formula. And if you think that positive formulae such that there exists are given primitive introduction rules, and the duals are their rules are just defined by duality. So how would you prove a for all? A for all would be anything that can consume a witness. Sorry, maybe it's hard to speak without. Yeah, actually, it's that's what I'm talking about. So for first order logic, it's very natural to say, well, the way that you decompose of there exists an X such that A is by giving a witness for X and a proof for A of that witness. Okay. Now, if you were to look at what rule would be inferred from that one for the dual of there exists, namely for X something, then you would be able to give a different proof for the different R's, for the different witnesses that you would have here. And this is not really what how proofs of for all works in logic. You really want to reason uniformly over the for all variable and not have a different proofs for the different ways in which you could instantiate this this variable. So anyway, that's just to close the parenthesis on going to first order logic and noticing that there's a little story there that's not completely trivial, to add the quantifiers and end up with the standard for all rule and not the omega rule from Frege and Schutter. Anyway, so that's for first order logic. Now, I have also in the document I describe how to instantiate the parameters of this abstract focusing system in order to have a two-sided classical focused sequent calculus, a one-sided focused classical focused sequent calculus, and a two-sided, because it's always two-sided in intuitionistic logic, a two-sided focused sequent calculus for intuitionistic logic. So those are the three instances that I have. And I don't know if I can instantiate my parameters in more subtle ways in order to get something like linear logic or sub... I've lost the words, what you were mentioning. Substructural logic. Yeah, exactly. So
model logic and this kind of thing.
Yeah. So that's, I don't know. Yeah. Maybe the framework needs to be even further generalized or tweaked to handle things like linearity and the substructural relation between exponentials and stuff. I don't think it can natively host them as a direct instance, but I'm not completely sure.
Yeah, I'm sorry. I mean, just to complement, because the thing is that I think that Kostov and Lutz, they used some of your ideas on systems, model systems, right?
Okay.
But not for sequent calculus. For I'm not talking about realizability. I'm talking about this notion that you have of separating the phases into two, and more or less like hiding some things, and then only talking about interfaces in focusing. Yeah. And so they apply this kind of ideas for nested systems for modal logics, but not for sequent calculus. So I was wondering if you ever thought about this as well.
Yeah, not exactly. I think, yeah. I suspect that there may be some modifications to make in order to support modalities, basically, whether they are linear logic exponentials or whether they are actual modalities from modal logic.
Okay, thanks.
Well, if you are going to think about extensions, Stéphane, kind of think about full intuitionistic logic as well, which is a version of intuitionistic logic that needs dependencies. That should be interesting.
What do you mean by dependencies?
I mean that instead of having, like you have in Meyer-Harris system, that all the rules are gammas and deltas except the rule for implication and for all quantification, you now have a more refined view where you keep noticing where things are coming from, and then you can do lambda abstraction if the variable does not occur in the rest of the delta. So this is something that Luis Carlos and I did a while back, 1994. And I think it's an interesting thing because it shows that intuitionism is not about having a single formula on the conclusion, which is kind of obvious, really, but lots of people still think that this is the case. So it is the system.
So the version, the version of intuitionistic logic that I have as an instance of abstract focusing is the one based on this grammar for formulae. So there's like the usual set of connectives, including implication, the bottom negation, etc. And the way that the abstract focusing system that I have can capture the notion of intuitionistic probability is precisely by tweaking this context extension operation. Because basically, for intuitionistic logic, what happens here is that some of the things that you're adding in delta are going to hide some of the things that you had in gamma. So after you've done this extension, you have no longer access to the things to some of the things in gamma, which may be related to the kind of dependency that you're talking about.
Look
I'm not sure.
possible to be that it is exactly the same. I don't know. I can send you the paper later on if it's easier for you.
Definitely. Yeah, but definitely in the case of intuitionistic logic, context extension is not just aggregating two lists. It definitely has an effect of shadowing things.
Correct. Thank you.
So yeah, I'd have a look.
Any other question or comments? No. So thank you very much again, Stéphane. It was a very nice talk.
Thank you.
And thank you very much, everybody who come here. A really short announcement. I would like to thank you very much, all of the speakers and all of the attendants for all of these talks. This is the last talk of the year. After 36 talks, we will have a break. Petrus decided that we will come back on February, and we already have 4 talks scheduled for the next year, beginning with Richard Epstein on February 11th. So thank you very much, everybody.
Thanks.
Thank you,
bye.
Bruno. Thank you, Bruno.
Bye-bye.